So our next and final speaker of the program is Eva Tardos from Cornell University. Eva is one of the founding figures of algorithmic game theory from the beginning. Her initial work looking at price of anarchy sort of generated a lot of the enthusiasm of that field that is very much alive and taking on a new turn that Eva's work has led, moving from analyzing games of complete information like the routing games that she and Tim Roughgarden started out with, to analyzing auction games of incomplete information. And that's sort of been very, very interesting from a mechanism design point of view, which is why I got very interested in a lot of the stuff she's been doing in the last 5 years. She, again, with Tim Roughgarden, was recognized with the Gödel Prize for her work on making Price of Anarchy what it is. She's also been working on looking at connections between learning agents playing in games, work that Avram Blum did some of the initial work for, and now Eva's been working on that space and looking at Price of Anarchy in correlated equilibria and outcomes of learning games. And so it's really great to have her talk about her latest stuff here, connecting, doing econometrics with learning agents. Thank you.
Yes, thank you, Jason. So thank you. So I guess when Jason started to talk this morning about how this econ or incentive and game theory-based area is tricky for understanding data because it's a selfishly generated data, and therefore, when you change the mechanism, the data might change with it. Or more precisely, what we mean is that the agents will behave differently. One nice way to kind of sidestep this, if your mechanism is incentive compatible, and then you can somehow hope that people will behave truthfully in just revealing their value. I'm going to actually talk about non-incentive compatible mechanisms. So I'm going to try to exactly talk about when what you see is not the agent's value. You know it's not the agent's value. Only an idiot would put their value in this kind of environment. So you know for sure that the values they're putting in are probably shaded, and the actual values are higher than this. And what I mean as the topic here is trying to infer what the value is. So the context that all of the experiments or all of the data I'm looking at is internet advertisements or variations on what's called generalized second price. I'll define in a second, or at least somewhat define in a second, what I mean by generalized second price. But this is the way advertisements is sold on the internet, a particular format of an auction that's not quite truthful. That is, there are reasonable bidding systems, but telling your true value is not the thing to do. Another feature of this environment is that it happens an awful lot. That is, it's repeated over and over again. For any particular keyword, especially the popular keyword, there are millions of auctions happening every minute, or certainly very, very frequently. And the advertisers can join the system and leave the system, change the system. They might not be aware of their value, or maybe they are aware of their value, who knows. And the system is dynamic in an over time fashion. As Jason was nice to put in his introduction, and actually you heard some extent, maybe Tim mentioned this too, there have been a long, maybe more than 15 years, literature on trying to evaluate mostly, for example, the price of energy or the revenue or this kind of auctions. And what this does is gives bands of the kind that maybe Ehud very politely criticized, a constant factor off from optimum, guarantees that the outcome of these auctions are reasonably good whatever reasonably good means here. And I guess what sort of bothered many of us, or certainly the research trend that I'm trying to talk about, is that it's very hard to evaluate this theory. So if I take the analogy with approximation algorithms, which works exactly the same way, it gets input, and because the problem is computationally hard in that case, instead of outputting the true correct answer, it outputs an approximation to the correct answer. There's a lot of empirical evidence that when you try these approximations, then they turn out to be so much better than what the worst case theory predicts. So we prove a theorem that this is, a factor of 2 from optimum, and then gets tried out in practice, and it's, 98%, very close to optimum. Not the true optimum, but very, really close to it. And I would love to do the same thing here. I would love to tell you all, or tell the community, that yes, this price of energy is a worst case estimate, and as a result, it's not actually optimum. And as Tim pointed out, it's quite often at least a factor of 2 off, and often even worse than that. But if you try this out in practice, then of course the insight that caused us to understand how good that this mechanism is not arbitrarily bad makes them actually a lot better. But there is a difficulty, and we have a lot of data, so we could look at things. But there is a giant difficulty, which is what this talk will be about. We don't actually have the input. So when you normally think of any input of how well our theory or how well theory matches, we would want to know what was the agent's valuation, and then we want to sort of say that, look, true, we only proved the factor of 2 bound, but then I ran on this particular one instance in a lot of computation time. I figured out what the true optimum is, maybe using integer programming or something. I figured out what the true optimum is, and we're 90% there, 95% there. But we don't know because we don't know what their values are. So this is what I want to talk about. The field that classically deals with this is called econometrics, and what it does is see the agent's behavior, and you want to infer the value from the behavior. And there is a whole big literature, which I'm going to very oversimplify on what it classically does to offer you a departure point of what we're trying to do differently. So here is the setup that we see. Here is a bunch of bidders here. Maybe they're bidding for this adduction. For this picture, it doesn't matter. You should imagine this being over time. I'm bad with this, so I guess time goes maybe from here to there. The bidders show up, bid something. Maybe, as Avrum's example also suggests, you see them winning the auction. Maybe you see the price. I don't know what you saw. You saw something. But what your goal is here to infer their values. And unlike in Avrum's case, I gave you nothing about their values. Maybe I gave you the second price, or maybe I just gave you the winners. What I really give you, and that's the data that Google or Microsoft or these companies have inside, I gave you their bits. I know what their values are. I gave you their bits. Avrum was running a truthful mechanism. So therefore, he could reasonably assume that their bits were the true values. But the way I want to make this more complicated is I actually make it simpler. I give you all the bits, so you Google. You see the whole thing, not just the winners. But those are the bits. Those are not the values. And your job is to infer the values. OK, so the most important thing is that the values and the bits are different, and you're supposed to infer them from each other. So this is like hopeless unless you make some assumptions about the bidders. If the bidder is bidding 17, no matter what their value is, of course, there's not enough information there to infer their value. So you have to make some behavioral assumption. And econometrics as a field, the traditional assumption is that the behavior is a Bayes-Nash equilibrium. Equilibrium of some sort, maybe more commonly Bayes-Nash equilibrium. What that means is that players best respond to the distribution of bits of their opponents. So let me actually make it concrete with maybe thinking about 2 different papers that did this in the adduction setting before I offer you the point of departure that maybe this simple Nash equilibrium assumption is not matching the data all that well. But before I even go there, maybe it's useful to say the one sentence that's common in a lot of what the 3 of us are talking about. I'm going to here now change that rather than me, I wanted to learn something from the data, which I do. I also want to make the assumption the agents themselves are learning also. So I want to depart from the assumption that they magically, in their head, computed a Nash equilibrium, and rather change that assumption to say that they're learning too. But before I go there, let's actually go with the standard econometric assumption that there is a Nash equilibrium. So let me give you a little bit about what this sponsored search auction looks like. So there are these positions that people are bidding to put their ads in each of these various positions. Generally, there is a quality factor or some sort of quality score that the ads get. If you want, you can think of the quality score as some sort of number that represents how clickable those ads are, because as it turns out, payment depends on getting clicked on. If you don't like it that way, for this purpose, you can think of quality score as simply Google's or Microsoft estimate how reasonable the ad is to match the query. It is not in anyone's interest to, whatever the ad is here about, to put up irrelevant ads. That's not good for Microsoft, it's not good for the payment, it's not good for us as viewers. So there is a giant part of Google or Microsoft or any company that's doing this. Ad placement department is trying to figure out these quality scores, figure out an automated way of how good these ads are. And what they do is take the bits, multiply it by quality score, and sort by that, and then put in the better or higher probability click positions closer to the top of the page, ones which has a higher score. Okay, this is the classical ad auction. I guess technically there's a payment part, or not technically there's a payment part, and what you pay is the next highest bid, if you want to think about it that way, or the lowest bid you can put in to keep your position. Yes. Sorry, the two of you are asking questions simultaneously. Could you see questions? I'm going to think of this as a repeated game. The same bidder is participating. I'll come back to that point in a little bit. Yeah. They know they quality score. They both are great questions. So actually, so a good question was, I'm going to, for at least the large part, almost all of this talk, I'm mentioning some work that doesn't have this, but for most of this talk, I'm going to assume that it's the same set of bidders participate repeatedly over and over again, and they will have, for this purpose of this talk, not all of the work relevant, we'll have a fixed value V. A quality score might be variable. And then there are two versions here on the quality score, and that answers your question. There is the full information version where the quality score is known, or at least they repeatedly play with the same quality score, so they should be able to learn it. And then there is the version that the quality score itself is variable. And this is actually a big distinction in two lines of work that is the first thing I want to emphasize. So the first version of this, where the quality score is viewed as a fixed, something that the bidders can know or certainly can learn over time, is when the quality scores are fixed quantities, same players play over and over again, and you think of it as a generalization of the second price auction. The regular single item second price auction, that is assuming there was a single spot here, would just take the one with the biggest quality score and play the second highest price. And the generalization here is that there are many more spots that are less and lesser quality, and they're all paying the next highest price. The actual details actually won't matter of how this auction works, but maybe some of you know it, some of you don't, and it really won't matter so much. So the first papers in this area that got a lot of us excited that there's something really interesting going on are a pair of papers, Varian and Edelman, Ostrovsky, Schwartz, around 07. I'm not sure exactly what the right dates are. That they thought about this as a full information game, that is both quality scores and values and everything is stable, and pointed out that there is a socially optimal equilibrium here. That is, truthful bidding is not equilibrium. You're supposed to shade your bid. But there is a Nash equilibrium that actually socially efficient, which in this case means actually truly sorts people in the value times quality score order. That is, higher people with higher values bid higher, not their value, something lower. Varian actually also points out that watching people bid, or watching this equilibrium bid, you can somewhat infer their value. You can't infer it exactly. You can infer ranges on the values. And basically, it gets inferred from something, something really kind of simple. It gets inferred from the fact that if you prefer your slot, your value is such that you wouldn't prefer a higher slot or a lower slot at a higher price. Gives you inequalities on what the price is. So if you think about this equilibrium as a prediction of what should happen, then if it's a stable set of participants and a stable set of quality factors, you should see that the prediction is that the bits are stable, that they don't change over time. And in fact, both of these papers point out that this generalized second price is much, much better than its predecessor, which was the first price, where people were simply making bid their own value, which was super unstable. The bits were oscillating like crazy. This is a ton more stable than that. And that's what they were doing. And as I said, variance also points out that you can infer ranges of values. Okay. Now, I got interested in this area of trying to infer values in a paper by Etty and Nekipelov, which actually both introduced this uncertainty about the quality factor and offered us a way to infer values exactly, not ranges, but precisely pinpoint the values. So they pointed out that, yes, it's true if you think of common advertising items, such as, for example, pizza or flowers or something that people buy a lot on the internet. Indeed, the bidders are well known. I don't actually know who are the pizza deliverers here, but I bet everyone else in the room does. There are a few companies that would deliver pizza here, and those are the ones that are advertising. So that's indeed a full information game, the same set of players playing over and over again. But the quality factors turn out not to be actually so stable, and that's the good question. The quality factors, usually these companies have like ginormous machine learning departments that that tune a very sophisticated machine learning algorithm to figure out quality factors. And the way to think about this, quality factor depends on an awful lot of things. Like, you know, maybe I don't actually know these things, but maybe the style of machine you search from does signal whether you're a student or not, and hence would tell them whether you're likely to buy pizza or not. Or maybe definitely the time of day matters, definitely your physical location matters. Some things are better than other things. And so the quality factors are not at all fixed depending only on the person, but depends on other parameters of who the searcher is, the time of day, and other kind of things. So what Susan and Etty and Nekipelov are suggesting is that we should model the quality factors as a draw from a random distribution, sort of a mix between a Bayesian model and a full information model. The values might be full information, but the quality factors are Bayesian or randomly pooled. And then I guess in their case would suggest that you're bidding to maximize your expected utility given the randomness inherent in the rest of the system. The prediction still would be that you should get a stable Nash equilibrium, and here is how they try to think about, and here is the moment you no longer have to actually remember how this generalized second price auction went. What you should remember is depending how good a position you're getting, which would be higher or lower, there is a certain probability that someone actually will click on your ad. Okay, that I'm going to call it as PIB, is the probability that with bid B you get clicked on. And then there is also a certain cost that you should expect to pay for if you put this bid B. And rather than, I know with bid B you might get the top position or not the top position, but these are random things because it depended on the quality factor. So I cannot think of this as a function from bids to the probability, indirectly to the probability that you get clicked on, sidestepping which position you got into, or integrating at which position you got. And then we say that your utility for the reward for what you got is your value for a click, which is the expected buying power of the person, times the probability that you clicked on minus what you had to pay. And what they observed in data, and I'll show you some data from the Microsoft data we're looking at, that in big auctions, that is commonly running auctions, the CNP functions are actually continuous functions, very smooth continuous functions. And if that's the case, that is the probability of the click as a function of your bid and the cost both are continuous functions, then this is a really simple equation to invert, and in fact, I could do that. I see, I should have pointed out the quality score being random, what causes the functions to be continuous. And I can simply solve this equation for what the optimal bid is. Okay, this is a very simple linear equation on the value. You can solve. Your bid must be that bid that optimizes this, if you correctly optimize it. And in fact, then it allows me to infer your value. I know what you're bidding, and I know what value that corresponds to. Yeah? Yes. So,
if I increase my B, at some point I will win, and at some point I lose the option. Is that okay?
yeah, so this is an excellent point, and maybe it's good to slow down a little bit to make sure everyone is with me on this. So when I change my, if everyone else is fixed, quality source fixed, everything fixed, if I change my bid, then these functions, both of them, are extremely not continuous. Okay, what happens is, at some point, I went above Ehud's bid, which means I went a better spot that Ehud used to have a second ago, and therefore my probability of getting clicked on went from 0.7 to 0.9 because that's a better slot. And the price, I used to pay some low price, but from now on I'm above Ehud, I have to pay his price. Okay, so this is very not continuous. But with the quality factors in, if the quality factor, I don't know whether I went above Ehud. With some bid, I have a 0.7 chance of going above Ehud. And in another bid, I have a 0.7.1, a little bit more chance of going above Ehud. Our ordering, if our bids are such that we should be close to each other, is a random thing. And by increasing my bid, I'm simply pushing up my probability that I went above him. And that randomness causes both of these functions to become continuous. The Atti-Nakipalo paper works out some sort of mathematical assumption that they're continuous, which I'm going to sidestep here. I'm going to show you data. Look, it's continuous. But indeed, if I make a strong enough assumption of how big the range of the scores are and how smooth it's over that range, then you can indeed prove that the functions will have to come out continuous. Okay, that's.
And the randomness in the scores, it comes from the algorithm?
Yeah, the proposal is, so the score is computed by a machine learning algorithm. So they take, say, I order pizza from my laptop. They take all the information that my laptop gives them about me, how often I ordered pizza, who am I, where am I logging in from, what laptop I have, whatever other garbage they have about me, which is an infinite amount, feed it into a machine learning algorithm. Technically, what I'm assuming in this model is that the machine learning algorithm is really, really good. They actually have it 100% correct what the quality of this ad is for me personally. But machine learnings are very good. This is a very successful field of research. So it's not a crazy assumption that they're really good at this. But I'm also assuming that what machine learning is really bad at is telling me what that factor will be. It has the factor right, but it can't explain it to me. And one evidence I have for this, that if what the feedback Google gives to advertisers about the quality factor is indeed not a number because it's varying, but statistical information about that number. So Google's feedback treating the quality number as if it was a random variable. So therefore, me too in my model will treat it as a random variable, which you cannot know because that's what machine learning is bad at, explaining to you what's happening. It can give you statistical information about it. I'm going to treat it as a random variable. Okay, that's actually Susan Etty and Nagipalov treated that way too. So the assumption here is that the quality factor that caused you to be certain order is a variable whose distribution you know, but you don't actually, that's a random pool from the distribution, and repeated random pools are independent. Okay. So I want to finish. This is again still Nash equilibrium based assumption, and in fact, there is something stronger comes out here because these two functions being continuous. Then we can simply solve for what should be the equilibrium bidding function for any value v what you should bid. Simply, it's a linear equation. You should, or not linear in v. Non-linear in B's, but it's a continuous equation. You set the derivative equals to 0. That tells you what to bid. That gives you a bidding function, and then all you have to do is invert it. You know what the guy bid, tells you what his value is. One funny aspect of what's coming out of this paper is that if people actually are changing their bid, the prediction should be that the system should be at Nash equilibrium, and they should not be changing their bids. If they are changing their bids, then I guess my inferred value keeps changing. So there is this pizza store, and for some reason, using the Etty-Nagipalov machinery, I'm going to conclude that every 10 seconds, the value for a bid changes. Doesn't seem very reasonable to me. And if you look at what Susan and Etty and Nagipalov are doing in the paper, they're taking all these inferred values and averaging it to actually give you a number, which I think it's not clear that there is a theoretical justification of why they average those numbers. So I would like to do something different, and I want to try to understand what's going on. And I guess one thing, this is two different bits from two different ads on Microsoft data over 7 days. These are, so they're looking at either side of the spot. So this red guy here is a bidder. He's changing this bid. The way Microsoft auction platform runs as a bidder, you can change your bid anytime you want. So for example, this guy for this long period chose not to change his bid, but here over he changed his bid a lot. You can log in anytime and change it. One would guess that given how frequently these fellows are changing their bids, this is not a human, this is an algorithmic bidder. But we're only inferring this from the data. That is, we're thinking that someone who's changing this bid more than 4 or 5 times a day, that's probably not a human. That's probably automated bidding. Yeah. That's what they're thinking. Yeah, that's what they're inferring. It's a Nash equilibrium of a one-shot game. Every moment in time, you're best responding to the distribution that's happening, not that very short period. They're taking like a couple minutes, and they're thinking every minute you best respond to what's happening in that minute. That's what they're doing. That would have their value vary, and then they average those values. Yes? No. The hope, again, is these are not budgeted bidders. These are really big customers with very big budgets and very frequent bid changers. So yes, there's another issue here with the budget that I'm eliminated at by looking at bidders who have very, very big budgets. So if I stare at what's going on here, and this is not a mathematical statement, but a sort of intuitive statement, I think they're running a learning algorithm. They're running a gradient descent optimization kind of thing. They're trying to, make David go up, or especially this guy here. When it go up, then he seemed like he overshot, then coming down again. He's like someone gradually adjusting their bid. It's much better match to this to me than there's a different equilibrium going on every day even, or every couple of minutes. So I think that's a better match to this data that they're running a learning algorithm. So what we're hoping to do is actually replacing the equilibrium assumption with a learning assumption. And I guess I have a couple suggestions of why you might want to do this. First of all, there are companies out there who you can hire to do the learning for you. So again, these look to me like automated bidders. I'm thinking they hired one of these companies to automate the bidding for them. I don't know. That's a guess. Second, there's the repeated game question that Ehud was getting to. This is a repeated game. And again, I have to make a behavioral assumption. And I guess the way the Etienne-Nephi-Pelov or even the Edelman-Ostrovsky-Schwarzovorian assumption is that they repeatedly paying the equilibrium of the one-shot game. Maybe, I don't know. I'm going to today instead assume they're running a learning algorithm. They take the data from previous day and they're trying to figure out how to best respond to the data from previous days. They're not maybe trying to run inference and figuring out the Nash equilibrium. They're simply trying to learn. Because at the end, it doesn't matter to me what your value is. What matters to me what you're bidding. That's what I need to win. Learning has the advantage because a couple of very clear advantages in this situation. It's a great way to adapt to the opponent. It doesn't matter what you should bid in equilibrium. What matters what you are bidding. So if you're bidding badly, I should take advantage of that. I don't need to have a common prior. I simply watch what's going on. I guess I sort of repeated takes advantage of the opponent playing badly, and instead I'm missing very minimal feedback. Learning algorithm just needs utility feedback to me. I bid something, I see what happens. I bid something else, I see what happens. That's what learning algorithms need. And that's going to be my assumption, and I guess to make it concrete. So here is a repeated interaction with agents learning. Action repeated over and over again. There's something happens. And what we want to emphasize is the bits are not the values, and what we're hoping to assume that these are the basic mathematical assumptions. Assume that it's the same game each period. This comes back to a Hoots question, which I will tangentially mention as a related work or something that would be nice to figure out. As I mentioned in the beginning, there's some dynamic aspect here. People come and go, and would be nice to observe that in the data. And I'm going to assume that the value is additive over periods. I think this is very reasonable on this sort of very small items. I'm going to assume that over time they're learning, they're trying to have a better idea of how to bid. I assume they're using a learning algorithm and update strategy based on past observation, and they learn how to play reasonably well over time. What do I mean by reasonably well over time? So now back to what did I mean when it was Nash equilibrium. When I talked about Nash equilibrium, what I meant is, or what Susan Etienne-Nephi-Pelov or Varian and Edelman-Shofsky meant is the equilibrium of a one-shot game. This is what that would mean in plain English in a repeated setting. They do something up front, who knows, they didn't know how to do, and here they got to an equilibrium. That means they repeat the very same action over and over, and that action is a Nash equilibrium, which means the utility gaining is bigger than utility of any other action. This is definition of Nash. What I showed you is evidence that this is not happening. They're not bidding the same thing over and over again. I'm going to call this Nash equilibrium property a no-regret property, and what I want to do, step number one, is generalize it to have a no-regret property without that stability of repeating the same thing over and over again. So no regret here meant that the action that they take is better than any other action, and I also meant the stability assumption. I want to get rid of stability. What getting rid of stability here means is that the utility, and this is what I will mean, utility of what they're getting, which may or may not be stable, is better than any fixed action with hindsight. Better than any single action with hindsight. Or more technically, I'm going to call the regret. If that's not the case, if there is a single action that had they played consistently would always be better than what they're paying, I would say that that's a regret. And what I want to assume that this regret is small, that it doesn't go linearly over time. And there are many, many algorithms out there that keep this regret roughly root t, that over time t, like you can add one extra regret every single time step, you can get it down to sublinear. In particular, a root t size of regret growth is easy to achieve, and many, many algorithms do that. And what I want to do is take the Nash equilibrium assumption and replace it with this no regret assumption. And I want to do that because A, algorithmically, it seems to be more doable than Nash equilibrium, and B, because I claim it's a better match to the data. there is no stability in the data, and therefore I like something that doesn't assume stability. And I'm going to ask 2 questions, and I guess I didn't actually remember when I started. I have like five-ish minutes. I want to 10 minutes. Okay, excellent, lots of time. So I want to give you 2 things. I want to talk a little bit, and that's a part of the talk that I'm more just referencing, that there's a lot of existing work in the theory community talking about what we can say about games with this assumption on behavior. And what I want to talk about is the inference that is getting the value out of the player with this assumption as a behavior. So I'm going to skip the how this looks in a concrete game due to lack of time. So I want to say that the whole question of what happens in games if everyone does learning is a well studied over the last, again, roughly 15 years. And mostly started by, I got interested in this in a talk that Avram gave a long, long time ago. And there is a beautiful paper, a team that's summarizing and highlighting a lot of this work and explaining how general it is. Extending price of energy, that is quality of the solution work, to when the player is doing learning rather than getting Nash equilibrium. It's a repeated game setting, and more recently, and this is work I won't be able to talk about, even when the player population changes. So even if I do actually model the thing that's really happening, players come and go. Even then, we can prove that there's high efficiency. They achieve high efficiency. What I want to focus on today is, can we infer the values? That is, can I say something about how these, what the player's values might have been? And that turns out to work sort of roughly the same way, at least the Atty and Nekipelov line of work. It works very similarly, and let me try to tell you how this works. So I wrote again down the no-regret assumption. And no-regret assumption said that, and oops, I've changed it here, bits instead of actions. You do bits over time, and you're getting some sort of valuations out of utility out of your bits. And to be a little bit more formal, because I don't know your value, I put your value into the utility function. So your utility, of course, depends on what you're bidding. But it also depends on the secret value, which I would like to infer, so I put it back in the notation. And we claim, because of the no-regret assumption, that this is better than a single bid with hindsight, minus a little error. So I take this inequality and want to say, OK, so given that I know the bit sequence and I know that you should have this property, what are the values that might be reasonable for you to have? And if I, instead of this little o of 1, I just put in an explicit epsilon here, then you could say absolutely, of course, absolutely anything that is reasonable here, because it depends how big the epsilon is. With very big errors, anything can happen. But it gives you an inequality that connects values to this epsilon. And if I actually put back the same inequality that we had from the Atty-Nekipelov line of work, instead of probability of click, I now want to say how much more click would you have gotten had you fixed bid epsilon, or how much more would you have to pay if you fixedly bid X all the time. Then I get a very, very simple inequality. Had you bid fixed epsilon X all the time, your probability of click would have gone up by this much, so that value went up by this much. You would have to pay this much more, and apparently, if you have no regret, this should be less than epsilon. This is how much you gained. Your value went up by this much. The price only went up by this much. This is your gain here. This should be less than epsilon. This is a very nice, simple inequality in a value, which I can use to infer not your value, but rather a value and epsilon pair for you. And here is my data showing to you that this click and probability price are actually super smooth and continuous. So the assumptions were actually very much matching data. If I look at these inequalities, I can put a 2D plane on it, value and epsilon error. And every one of these is giving me a linear inequality in epsilon v pair. This is a linear equation in epsilon and v. So I said, OK, if this has to be true, I have to be on that side. And so I get is what we call the rationalizable set, the possible epsilon v values that would satisfy that inequality. If I look at data, and this is actually data, the only thing hidden here is the values are normalized to some 1. So I and the rest of you who are not working for Microsoft are allowed to see what the values are. This is what we get as rationalizable sets. These are 2 actual examples. This rationalizable set, you feel like, oh, I see. Apparently, the error, this is the error thing here, the regret can go down almost to 0, so the value must be here. This guy is having no regret. Whereas this guy, you have to conclude, oops, he's definitely having regret. And you can step back and say that it may or may not be inferring the value correctly, but I definitely have it straight. This guy has regret. There's no value in the universe that gets him no regret. He definitely has regret. I may or may not have his value right. To actually have to match this with data, I want to spend, maybe if I have 2 more minutes, to tell you about 2 data sets, one from us and one from a very recent paper with Nissan and Naughty. Our data is coming from Microsoft, and I actually talked a lot about it. And Nissan and Naughty tried this out as a human subject experiment. As it turns out, they actually ran this a year or maybe 2 years ago, before we ever wrote this paper. But they went back to look at the data with our eyes and asked, can they infer the human subject's behavior in the real data? And I think it's nice to add one word from that. So our data set is 9 frequently bid-changing advertisers with giant budgets and good reason to believe that they're algorithmically bidding. And I'm going to actually more show you the statistical data. So this we get for regret. We get about 30% of the advertisers who regret is essentially minimal. Some of them might actually be negative or slightly negative. Actually, stop here. Negative regret is possible. Like you might actually take advantage of how other people are cycling their bids to always be on the right side of them. Negative regret is possible if you take advantage of the dynamic of the other people, and some people do have negative regret here. 70% do not, and it's sort of pretty evenly spread of what the regret values are. This is our prediction of shading their bid, and I think maybe the best spot is we're guessing that people with, given our prediction of their value or estimation of their value, there seems to be a slight correlation with people with higher regret shading their bid more. This would suggest that you start by actually bidding really low, and as you develop regret, you push it back up because it's a competitive market and they have to bid high. I'm not sure how strong this conclusion is. This line is not very straight. I want to spend couple more minutes on telling you a little bit about this recent paper of Noam Nissen and Gali Naughty, which is human subject experiment. I like our version because it's algorithmic, and as I point out in 1 second, there is an issue here that humans behave irrationally at some point, whereas algorithms, I hope, do not. I don't know. But it's interesting. They ran 4 sets of experiments, generalized sequence parts and VCG. VCG is good to point out that's a truthful action. You should bid your value there. Whatever VCG is, don't worry about the details. But that's one of those things that Tim and Avram like talking about. You should bid your true value. And what these people tell us, this is they ran 1,500 auctions over 25 minutes, the same Microsoft setup. Every bidder can change their bid anytime they want, and the auctions are running every second, whether you like it or not, whether you change your bid or not. So that's for 25 minutes at 1,500 auctions. This is the frequency of bid changes. It goes up towards the end of the 25 minutes. It does not stabilize, not even in VCG. Not even when they should be truthful. The VCG line here is, these 2 lines are VCG lines. They should be bidding a fixed number, they're not. So this stabilizing is just not happening, not even when it should be stabilizing. They actually, so the way it worked, they told people what their value is and asked them to participate in this auction with that value. So now we know what their value is because they were told what their value is. So you can also evaluate it compared to social welfare, and we know that we were 95%. Towards the end, we were 90 somewhat. All of the auctions are almost 100%. Like 100% would be up there. It's a little bit less. 92% of the social welfare, which I think is really nice. Human subjects do learn to minimize regret, except there is this one spot which I think I should point out. This is the kind of values they give people. And the high-valued people actually were good at pushing the regret down. The very low-valued people did not, and they explain it by those people losing all the time. It's a generalized price. They sometimes win the low spots and probably not winning a damn thing. And that's just so frustrating that they're behaving irrationally. So this is irrational human behavior done here. They think, and probably I think so too. And finally, actually, one interesting and maybe not so great spot for us, but I wanted to show that for full disclosure, is how good they actually have values. So they can ask, is my algorithm inferring the values? And they run it in our algorithm, that's the blue here. And this is the error bars, so lower is better. Our algorithm is a little better than inferring values than either the Varian version or the Atinakipalov version, which is yellow. Not as much better as I thought they would be. Except, please remember, they were nice to Varian and nice to Atinakipalov, who are taking varying values and simply took the average. So if I took the varying values, then we're much better. But if you average their values, on average, those values turn out to be pretty reasonable. So I'm going to stop here, and I guess I'm suggesting two different things. I very much like thinking about game theoretic interactions that are not truthful when I cannot assume that people are truly admitting their value. And I guess as you've seen in the Nissan and Gali experiments, even when they should be admitting truthfully, they might not. So it's not clear that that's always a good assumption. We have a lot of literature in trying to understand how good the interactions are when they're not truthful. But we need something like these econometric methods to infer the values to be able to try to evaluate how they really work in practice. And I guess two conclusions here. First of all, data said that many people have no regret. Not everyone does. Like I had about 20–30% of the people in the Microsoft data had high regret, and in the experiments also a lot of people did. The bits are not stable either at Microsoft or at the human subject experiment. So I think this is an important research to understand better. And I'm going to stop here. Thank you.
So I think we have maybe time for two questions, and then we should leave the room because there's a class in here at 12:30.
With the human subjects, were they told that BCG is good?
I think so. And actually, there is important, like, there is 4 lines here rather than 2. So they did VCG and GSP and told a version in which people were told their value and a version in which they were not told their value. They had to infer their value from the numbers they're getting. So in a version that you don't actually know your value, I know it's in the data. You can get it at. But that's an extra issue, whether people are good at inferring what their value was. I don't think they were taught powerful enough to convince them to do it. Yeah, I don't actually. I should check more carefully with Noam what they were taught. Yeah.
It's a question for Lawyer. The lower you equal I have a problem with the word neglect because it says that it should be immune to deviation to hindsight or demand. The constant side. In other words, I cannot go and change what I did period by period. I have to replace the whole past by X. So it's immune to constant change. So it could be thought of as a Nashi polynomial integrated game in which we are forced to
Yeah. Yeah. So you're completely right about the word, the naming problem. And I guess if algorithmically, these algorithms that achieve this property could also achieve more sophisticated properties, like if you would like on even days bid differently than odd days, then I can change my regret standard, as it's usually called, to have 2 bits, an even day bid and odd day bid, and I cannot regret that one. It's a bit harder algorithm.
I don't regret single change, then I'm making nice. No regret in the full sense would be nice.
Right, right. And what the algorithmically thinking about it, there are the so-called regret standards, or what are the things I'm hoping not to regret, and I have to keep the dimension or complexity of my regret standard low, going back to sort of definitions that Tim had, in order for this to be learnable. If I'm willing to change my bid every single day, that's not a learnable standard. That's too complex for learning. The single Davis hindsight is simple enough, but I can do more complicated things. This is a simple enough thing to look for, and my hope is that people might be doing more sophisticated things than this, but maybe they're doing at least this much. Like in the Microsoft data, which has days, as in Monday, Tuesday, Wednesday, it's not crazy that the name of the day should matter, and you should have a bidding standard where you're learning what to bid on Monday. And in fact, some people in the Microsoft data had negative regret, which presumably they're learning to a better standard than what I'm holding them to. In the Nissan data, no one had negative regret, and that's because they're literally repeating the same auction. They don't have day effects. So in order to get negative regret there, you have to learn the cycling of the other players. That's a much trickier business to do. And 0 humans had negative regret.
All right, let's
Okay.